Hello everyone. My name is Salvatore Vicinanza. I'm a master student at Delft University of Technology. And today I would like to present to you part of my research conducted on meteor spectroscopy. This was done in collaboration with ESA and particularly with the Meteor Research Group, which I will call in the following MRG, by the way. So this presentation actually will concentrate on the spectral calibration of meteors, and specifically I would discuss the procedure developed for an elevation-dependent atmospheric correction and demonstrate the improvements on spectral meteor spectral analysis deriving from the application of such a procedure. Before continuing, to avoid any confusion for the further understanding, I would like now to point out that for elevation dependence, we mean the actual dependence of the atmosphere on both the angular term of elevation, so the actual angle above the horizon, and also the linear term, so the elevation above sea level. So in this slide, you can see the actual outline of my presentation. Firstly, I will briefly introduce the experimental setup that we used in our research. Then I will locate this research in the context of past MRG research for meteor spectroscopy and highlight the challenge that we wanted to tackle, which is the atmospheric influence on meteor spectra. Then the spectral calibration is discussed, which represents actually the core of the presentation. Here, a procedure developed for elevation-dependent spectral calibration will be discussed. And finally, in the results and discussion section, I will show a test case, and this will be used to present the improvements on meteor spectral analysis and meteoroid compositional inference, which can derive from the application of such a spectral calibration procedure. So as already mentioned, this was a collaboration with the Meteor Research Group, and the MRG actually operates an observatory, double station observatory in the Canary Islands. This is called SILBO. So SILBO hosts image intensified CCD video cameras in both La Palma and Tenerife. For this research, we mostly concentrate on the Tenerife station, particularly on the ICC8 camera, which is here shown in a sketch in a block diagram. This camera has a transmission grating mounted on top of the camera, and this is placed for maximal efficiency at the first order. So through it, we can see the first order spectra of meteors. A typical meteor event observed by ICC8 actually observes around 30 to 50 video frames with a frame rate of 25 frames per second. And a meteor generally, but it also depends on the meteor speed, but generally this goes through around 1 kilometer in the atmosphere between consecutive frames. This is an interesting point because it means that at the end of the path observed by ICC8, the meteor could have also gone through more than 30 or 50 kilometers in the atmosphere, and this is of interest to take into account for considerations about the elevation, the altitude dependence of the spectral calibration. So, but how and why did this research start? So to understand this, let's first have a look at past research within the MRG for meteor spectroscopy, which focused actually on the spectral analysis of features within the limited range of 400-800 nanometers. And also the analysis was done on a limited set of events. We're talking about the order of 50 events analyzed. It's important to point out that in the spectral analysis, no atmospheric calibration was applied initially. And also features outside of the 400-800 nanometer range were considered initially negligible for these past studies because of the limited sensitivity of ICC8 at these wavelengths. So through a laboratory calibration, it was obtained previously, actually more than 10 years ago, a sensitivity curve of ICC8, and this suggested that ICC8 could only record features within 400-800 nanometers. So thanks to the automation of the data reduction pipeline in this research, it was then possible to actually extend the analysis over more than 350 new meteor spectra were analyzed. And from this set, something was seen that actually for some events, it was noted that the intensity outside of this 400 and 100 nanometer range was significant in some cases. And this is, for example, the case of this figure here. You can see here the calibration box limited to 400 and 100 nanometers. And for this event, you can see there are actually significant features even outside of this box. However, what was peculiar is that this behavior was not seen for all of the events. So a question arose, which was why this behavior happens differently depending on the specific cases. And of course, there can be a different meteoroid composition, but maybe there is some other cause behind this. And particularly in this research, we wanted to focus on the atmospheric extinction that, as I already said, was not corrected for initially. But before saying that, the first modification of this research was actually analyzing spectra of meteors over an enlarged wavelength range of interest. And this led also to a new characterization of ICC8 instrument response curve for the sensitivity. And so the actual focus of the analysis was the investigation of the influence of the atmosphere on meteor spectra, which, as said, was overlooked by previous MRG research. So we know that the Earth's atmosphere imposes a challenge on the accuracy of meteor spectral analysis. Specifically, the atmosphere influences the light which is transmitted from a meteor to the observing camera, and this is due to absorption and scattering of the atoms and molecules in the atmosphere. And because of this, the meteor spectra are then finally different as observed from ground than what would be the spectrum observed in space, for example. So an atmospheric calibration is necessary actually to accurately infer meteoroids composition from meteor spectra. However, the atmospheric extinction varies along the meteor's path, and precisely there is a dependence on the meteor's elevation. And this means that an accurate atmospheric calibration should, in theory, differ depending on the position and the time at which the observation occurs, and specifically, this should change depending on the elevation of the meteor in that specific frame observed. But the question was, are these changes, or are there significant advantages on the accuracy of a meteoroid compositional inference if we apply such an elevation-dependent calibration? So to address this point, so actually we saw that from literature, although this is not a trivial point, realized this point is not generally investigated roughly in literature. And so we wanted to address this point, and to do so, we developed a procedure for elevation-dependent calibration. And further in this presentation, I will show a case study to uncover the effects of this procedure that can have on meteoroid compositional inference. So the procedure for atmospheric correction developed here was actually allowed to correct for the wavelength-specific extinction of all of the atmosphere between the meteor and ICC8 on ground. So actually a correction vector was generated for each frame which was recorded by ICC8 for each meteor event. By doing so, it is possible through this atmospheric correction to follow the meteor's path in the atmosphere, and therefore it generates different correction depending on the position of the meteor in the atmosphere. This correction vector is obtained following this equation, which is an adaptation of the extinction law, and it has a dependence on the elevation, as said, on both its angular and linear term. And an important assumption for the definition of this correction was that of a double layer atmosphere. Actually, we considered one layer placed at ICC8 fixed there. The second layer was actually moving with the meteor So actually there was a plane moving with the meteor, and it follows the meteor's path in the atmosphere, so it changes depending on the frame considered. And in this like movement of the plane of the meteor, it's where it relies the most significant dependence with the height. So the dependence with height is actually linked to the mostly to the variation of atmospheric pressure as the meteor travels inside of the atmosphere, where the pressure at ICC8 remains fixed, but the pressure at the meteor's location changes depending on where the meteor is seen. So it differs for each frame. The second step of the spectral calibration was actually the characterization of a new instrument response curve, because as I mentioned already, originally the sensitivity curve was already obtained from laboratory calibration, but the reliability of this curve was questioned by our new observations. So we decided to realize a new sensitivity curve. And the estimation of this new sensitivity curve for ICC8 was based on the comparison between first order observation of Vega as observed from SILBO and observations of reference spectrum of Vega, so obtained outside of the atmosphere in space. Specifically, the procedure developed for the new characterization is shown here. And so it is based on a retrieval of 4 good observations of Vega from ICC8. These were then reduced and calibrated. After the application of the atmospheric calibration, a median was taken of these 4 calibrated spectra. And the median, the resulting of the median is shown here in red. So this is the observed median spectrum. This spectrum was then compared to the reference true spectrum of Vega in space, which is shown in blue. And the ratio between the 2 spectra was then subject to a spline fitting algorithm, the polynomial fitting, and thus resulted in a spectral response curve, which was smoother. And finally, a normalization was applied, after which this green line was obtained, which represents the ICC8 spectral response curve. So for what concerns spectral calibration of meteors, this ICC8 spectral response curve is then multiplied by the elevation specific correction vector for the atmosphere generated for each frame. And this allows in the end to perform an elevation dependent spectral calibration. So to show the improvements on meteor spectral analysis, which derive from the, which can derive actually from the application of this new spectral calibration procedure, we showed results from a test case, and these results will be shown in the following slides. And so the test case considered is actually the one recorded by, collected by ICC8 on the 1st of June 2012 at 10:51 p.m. The events recorded was recorded over 37 frames, for each of which there was a spectral calibration, a tailored spectral calibration for each frame, which was applied. And it's interesting to point out that meteor over these 37 frames spanned over 21.5 kilometers. So here you can see the first order as observed from ICC8 for this event. So the scope of this part of the study was actually to investigate the significance of using an elevation-dependent spectral calibration on the accuracy of meteor spectral analysis. So the plot in this slide, you can see actually frame 34 of this test case event. And the plot is used to compare the line intensity of the meteor spectrum with and without the application of an elevation-dependent correction. So in particularly in blue, you can see the spectrum after an elevation-dependent correction was applied. In orange, instead, you see the spectrum if a unique calibration is applied over the total spectrum seen by ICC8. So if basically the frame-by-frame variation of atmospheric extinction was not considered in this case. It is seen that the elevation-dependent correction improved the line intensity estimation by an average of 20% for features below 400 nanometers, and this the significance of this result actually shows that it is can be important to use an elevation-dependent approach for the accuracy of meteoroid compositional inference, and also shows that applying a unique calibration for the atmosphere over the total spectrum can have significant errors in the end, can cause significant errors for the inference. So for time constraint, I will not treat in very detail this slide, but what I wanted to show was actually that compared to, as already said, previous MRG studies did not include an atmospheric calibration, but in the new research this was performed, and it was actually seen that the effects of the atmospheric calibration application were specifically important for elements that were emitting at low wavelengths. And if you consider the test case, for example, that we showed, and you take the number density estimation of elements before and after an atmospheric correction application, so using our pipeline and using the past pipeline from MRG, there is a difference in the number density estimations, and this difference averaged over the 37 frames shows that there is an increase in number density estimations for elements like iron or calcium that have also emissions at low wavelengths, and the increase is around 10% in their cases. So in summary, this research investigated the influence of atmospheric extinction on the appearance of meteor spectra. In particular, an elevation-dependent procedure for spectral calibration is developed, and this allows to correct for the varying extinction happening as the meteoroid is traveling inside of the atmosphere. It was noted from our research that the elevation dependence of atmospheric extinction is not often investigated like roughly in studies of meteor spectroscopy in literature. However, this research showed that its influence on the accuracy of meteoroid compositional inference is significant. And we showed that for the test case, there can be actually also an improvement in line intensity estimation by more than 20% below 400 nanometers. Finally, we showed how the application of an atmospheric calibration improved the MRG pipeline of meteor spectral analysis. Thank you all for your attention.